I guess the only thing I would say about it, we kind of had a difficulty today, so maybe in trying to think positively, since we had this late start, I will assume that many of you would have come in early this morning to get help on those doing them the long way, but you weren't able to because we had the late start. So we'll just go with that right now. Because if we truly had a regular starting time and you had that much difficulty with those problems, to just assume that we would spend a lot of class time going through them and that would take care of whatever difficulties you had, I think is an assumption you don't want to make. I have noticed this year that the numbers of people I've had coming in either before school or maybe at lunch is fairly low compared to many years. Maybe this is just a really smart group, and that's good, okay? I'm not so sure, I know you're smart, but I'm not so sure that that's the total explanation. So just kind of something to keep in the back of your mind. We are going to be doing a quiz. The weekend's kind of coming at a bad time, if that's possible. And Friday is probably rushing it a little bit. I don't like to do quizzes on Monday, but if it works that we have to, that's what we'll do. And it's looking like our quiz is going to be on Monday, okay? Friday, I think, would be pushing just a little bit too much. So, you know, the most people I've had in getting help was last Thursday. What happened last Thursday? Oh, we had a quiz, all right? The day of the quiz is probably not the only time people should be coming in getting a lot of help on things. It's probably a little late at that point. But anyway, my 2 cents on that. So if there's some of these things that are pressing and you're not getting it, I should be seeing you probably. Here's how the setup of this goes. The 1 over x, we set this up using the definition of the derivative. Now, I wrote this out a few years ago where I was doing it with getting a common denominator, x and x plus h, so I could put these together. So that means this one needs an x plus h, top and bottom, this one needs an x. Some of you, I mentioned bow tie the other day. So you take this times this, and that gives you the x plus h. Take this times this, that gives you the x up here, and then you have your common denominator there. Okay, so I know Mrs. Payne did that last year, so you might do that. Actually, the technique that I showed you yesterday, I think is still a little cleaner. So if I'll show you that again. So if you've got this common denominator of x and x plus h, then you can multiply that times the top and bottom as well. So I don't care if you want to bow tie or get common denominators or do what I'm suggesting here, which is clear out the fractions. I don't care. Use any of those techniques, whatever you like best. So this one, if I multiply here, what happens? The x plus h cancels, and I just get x, right? And then when I multiply here, what happens? Just the x cancels, and I get x plus h, right? And then that's all over this common denominator. So mine, it would actually look a little different than this. So if I did that, I would have the x plus h's cancel gives me x, and the x's cancel gives me x plus h. And then I would have down here, I would have h, x, and x plus h. So when I do the clear fractions thing, it would look a little bit like that. Okay, now if I went with the getting a common denominator, I'd have this, and then down here I've got to invert and multiply that h, so I've got to pull that h up here, which is what you see right there, and that's what I was doing on that one. But if I follow this line of work, the x's are going to cancel. I'll have x minus h. So the x's cancel. I end up with a negative h on top. And then that's going to cancel with that h. Oops, forgot the x. Put it over here. Then that h is going to cancel with that h right there. And so now I end up with negative 1 on top. And then when I plug in a 0, now's when we can plug in our 0 for h. What do we get down here? X squared. And so there is my final answer. And remember what we're doing our, we can check it with our shortcut derivative. So 1 over x is x to the negative 1. And so we know, according to the power rule we learned yesterday, that to do the derivative, we can bring that down in front, which would be negative 1, and then drop that to a negative 2. And sure enough, that is the same as what we ended up with right there. Okay? But you can go ahead and leave it like that. That's fine. All right? But we can tell that it is the same. All right, let's go down to this one. Now this is the one that people really fell apart on. This is the conjugate one. So we start with square root of x, and so I did see some people that did have this as their beginning right here. Okay, you had this for your beginning, which is good, and this is the conjugate, the a plus b times the a minus b. So we're going to hear some more about that today. But the reason you do that, you have radical minus a radical, you multiply times radical plus a radical. You change that to a plus. You don't change this thing inside here, but just there. When I FOIL this, what happens? Well, first times first, radical x plus h, that's just x plus h. The outers and inners drop out. And then last times last, I just get square root of x times square root of x, which is just minus x. And look what's going to happen. I'll have x plus h minus x, so the x's will disappear. And of course down here I just have h times that thing, right, which I just leave the bottom the way it was. And so now I have this h on top, and then this stuff on the bottom. Well, the h is canceled, right? So you can see that right down here. So the h is canceled. All right, and so when the h is canceled, right here, I just end up with 1 and then this. And now what do? Put the 0 in for h. So now that I've got it, now that I've canceled the h's, now I can put the 0 in for h. And down here I get square root of x plus square root of x, which is 1 over 2 square root of x. Okay? And then that becomes, if you want to, you don't have to, you can stop right there. But a square root is x to the 1/2, and since it's on the bottom, that's the same as x to the negative 1/2. So that's what it becomes. Remember what we started with. We started with square root of x, which is x to the 1/2. If you do our new shortcut on that, you bring the 1/2 down in front, that drops to a negative 1/2. Sure enough, it matches what our shortcut told us it should do. Those are two algebra techniques you need to be able to do, because these were two limit problems. They happen to be derivative problems by the definition. And that's what we're going to be focusing on today here in section 3. Okay? So, let's talk about one problem I wanted to in the book here, number 46. Let's talk about that one. And then we'll move on here today. You've got y equals, or f of x, I can't remember what they said, doesn't matter. Square root of x minus 3 all over x, and we were supposed to find y prime, correct? Problem. We only have one rule we've learned so far of how to do y prime, and that is the power rule. So the only thing we know how to deal with is if we have x raised to a power, other than sine or e to the x, right? So we have to get that as x raised to some power. So we have to do some algebra to it first. We have to do some rewriting to make it so it fits our rule. So we got two choices. We could take this x and bring it up here as x to the negative 1, and we could distribute it. That's actually my least favorite way of doing it. For some things we're going to be doing later on, the method of splitting up the fraction is what I would like to do. And I want to just show you this real quick. If you have 3 11ths plus 4 11ths, what does that equal? 7 11ths, because what you do is you add the 3 and the 4, right, and put it over 11. Now, what I want you to realize is what we're going to do is just the reverse of that. If you have a single denominator with multiple terms on top, you can split that apart in separate fractions. So if I have 3 plus 4 all over 11, I can put the 3 over the 11, I can put the 4 over the 11, right? So whenever you have a single denominator, you can split that fraction apart. Now, it doesn't work the other way. You can't take 11 over 3 plus 4, which is 11 sevenths, and you can't write that as 11 thirds plus 11 fourths, right? Everybody's okay with that? That would be bad. That's not the same as 11 sevenths. Okay, you cannot split up denominators, but you can take a single denominator and split it into multiple fractions. So that method is what I want to do here. So I'm going to take square root of x, which of course I know is x to the 1/2, and I'm going to put that over x, and then I'm going to put that over x. This is just a cleaner algebra method, especially for some stuff that we do later this year. So I think this is one we want. So when you see a single denominator and something like this, you want to think split it up. Split it up. Now what can we do with those powers? Subtract the power. So this becomes x to the negative 1/2, and this, I'll just move the x up top there, and this becomes 3x to the negative 1. Those are some algebra things you just have to know. You have to know about negative powers, and you have to know about fractional powers with square roots. If you want to come in and get some review on that, that's fine. Come in. But you've got to be able to do that in this class, okay? Absolutely just have to. All right, so now we've written it. All we've done is rewrite algebraically. That's all we've done is rewrite. Usually for me, it's not necessary to rewrite stuff for your final answer. I don't care about that. Okay, like on that last problem, we had negative 1 over x squared. You want to bring the x squared up top and write it x to the negative 2? I don't care. It's just rearranging stuff. Either way is fine for me. But there are problems where you have to be able to rearrange stuff or else you can't do the problem, right? So you rearrange if it's necessary to help you do the problem, but not so you give the answer to me necessarily. All right, so now notice I've labeled all three of those as y because we haven't done anything there. We haven't changed them other than rearrange them, okay? So this is still y. Now we're ready to do the derivative. So we bring that down. What's our new power? Right, because we're going to take negative 1/2 minus 1, right? So that's negative 3/2. And then we're going to bring that negative 1 down, makes it plus. And then that drops to negative 2. And there you go. And then you can stop. And so like Miranda asked a question here during lunch today. Do we have to take that back into the radical form like the original answer was? You know, I'm guessing your algebra teacher may have made you do that. Well, yeah, because in algebra you were just practicing rearranging stuff. That's good. And so if I was teaching algebra, I'd probably make you take this answer back and make it look like the original. If it had radicals, go back to radicals. Maybe keep positive powers in it. You know, yeah. But for us, I don't care about that, right? I mean, there's some algebra we've got to be able to do, but at some point, this is good enough. So we'll stop right there and just leave. Okay? All right. So if you've got some other ones, some other issues that you had there, we will, again, come in and see me. I think the rest of them were very similar kinds of things, just the powers and the shortcuts and that kind of stuff. All right, I've got our website up here. In case some of you have never been to it, hopefully that's because you haven't been gone and haven't needed to watch the videos or anything. Under Chapter 2, that would be where our current videos are being stored. Down here on homework, I've got, for example, on Monday, it says 2.1 homework questions. And then down here, it also says class notes. And so I do post, not every day, depends on what we had, but I'll post just a PDF of the stuff that we had during class if you ever need access to that. And then if we have worksheets or something like we will today, I'll try to remember to post a copy of that in there as well. So if you're gone, you'd have access to be able to see that. Okay? All right, and so there is a video that we're going to watch under web links. Down on web links, I have some things. When we, I'll talk about the quiz here in a minute. All right, and I'll show you some stuff there. So, where are we at? Well, we're going to do our quiz. It's going to be over the first three sections. We talked about 1 and 2. Let's review that. 1 was the definition of the derivative. F of A plus H minus F of A all over H, right? And you don't have to write it down. I'll put this up. We'll talk about this as the week goes on. We'll put down kind of here's what we need to know kind of thing. But just quickly, definition of derivative. F of A plus H minus F of A all over H. 2 points getting close, becoming 1, right? It's just a slope formula. And we did some stuff the long way, right? So on the quiz, you're probably going to have to do that, right? Going to have to be able to do the long way with something, okay? Either the slope at a point or like today, find the F prime of X. All right? So we'll practice that one. We'll do a few more. This new section 2.2 is where we learned the shortcut. We took that definition and we learned about the shortcut. And so most of this section was just doing some of these shortcut ones like the one we just did. That's going to be a pretty small part of the quiz. Now, I apologize. Some of you like that. You think that's pretty easy. So maybe that should be a big part of the quiz. But because we're going to expand that and do a lot more of those kind of things. Okay, and before Christmas, as a matter of fact, that's all Chapter 3 is adding to our list of derivative rules and practicing doing derivatives. And actually the rest, sections 5, 6, and 7 in this one is more about derivative of e to the x and sine and cosine and those other functions. Okay, so we'll get plenty of that. But before Christmas, we will have a quiz where that's all we do. Here's 10 problems. Here's a y equals, like the one we just did, number 46. Here's a y equals, you find y prime. Okay? And 10 problems, and we call it the gateway test. And gateway means there's a certain threshold you have to make to get through. Okay? So, in other words, you have to get 8 out of 10 right, or you have to take one again. You have to keep taking until you get 8 out of 10 right. Now, the sooner you get 8 out of 10 right, the higher your score. So if you get 8 out of 10 or better the first time, you get 30 out of 30 in the grade. Okay, which is pretty cool, right? There's some incentive there to really try to be ready. If you don't make 8 out of 10, you can take it again. If you get 8 out of 10 that time, then the grade goes down a little bit, and so forth. If you can't ever pass it, then you just take maybe your best score. So if your best score was 5 out of 10, that's what, 15 out of 30. Hopefully that doesn't happen. The only people that usually happens to are people that just don't want to try very hard, quite honestly. Okay. But the vast majority of you will do well on it, I think, and you'll pass it in one of the first couple of times. Okay. So we'll talk more about that. You can see on the web links, Derivative Practice 1, Derivative Practice 2. That's an online practice that you can do and those kind of things when we get to that point. So that's when we get closer to Christmas time. All right? So that's when we'll do most of our quizzing on these shortcuts and these rules. So small bit of that, maybe a couple problems on the quiz. So the long way, the shortcuts. A lot of the quiz is going to be what we're going to talk about today. 2.3, this idea of limits. All right? A little bit of a side trip. We just learned this definition of a derivative. It's got a limit in it. I said it's one of the most important definitions and formulas we'll have all year long. It involves a limit. Well, it might be important then that we talk about limits a little bit and understand what limits are all about and what we can do with them. So that's what we're going to talk about here for a little bit today. So I've got on the website, I've got another little video here about continuity, which is something we'll talk about tomorrow, and limits. And so they do a pretty good job of explaining this. Some of this will be a little bit familiar with what we've already been doing when we were working these the long way. Okay? For example, let me throw up here, before I start the video, let me put this problem up right here. This was number 43 in your homework yesterday. I think we actually worked it out. We did this. Help me out if I'm getting this wrong. Was this, you guys got your homework out? Does that look like number 43 yesterday? So it was f of x equals x cubed, and we were trying to find f prime of 4, right? So we set up this limit, right? According to the definition, right? So that 4 was the a, so that's a plus h, and this was 4 cubed. Okay, so we were trying to find this limit. Now, this limit happened to be the slope of this function at 4, right? And what did we get for an answer? Like 48, right? What we're going to do today is we're going to pretend, that we didn't even know about this. We're going to talk about this as if we did this last year in advanced math, because we could have done this problem without knowing anything about derivatives. It's just a plain old limit problem. But what does that mean, a plain old limit problem? Well, that's what they're going to talk about here in the video. And we're going to reference back to this as I try to show you what that means. All right? So, let's go ahead and get started on it. And you have access to these as well if you just come to the website and pull these up, and you can look at these. Okay? There's a website called calculushelp.com. These are some tutorials, some little videos, and there's some ones here on difference quotients, and we'll watch some other ones here, but we're going to watch these first 3 here real quick. They do a pretty good job of explaining some things here that I just like how they help you visualize. As soon as
You may have heard a lot of talk about limits, but the plain fact remains, most people don't understand what a limit is. So for now, we're going to focus on what is a limit. In basic terms, a limit is a height that a function intends to reach. That's pretty important, so let's say it one more time. A limit is the intended height of a function. Now this might give you pause. You might think, how am I supposed to know what height a function intends to reach? I don't even know what my intentions are most of the time. How am I supposed to discern the intentions of a function? That's a good question. And the fact that you don't understand exactly what I'm talking about is because all of the functions you've been dealing with, or at least most of them, have had their intentions completely clear. If a function intends to reach 3, it reaches 3. If a function intends to go 6 units high, it goes 6 units high. There hasn't been a lot of mystery so far. So I understand that you might be a little confused, but you've dealt with function heights a lot, so we might as well review function heights a little bit and then get into exactly what I mean by intending to go to a certain height.
Okay, so I really like how they present that, the idea of a function. Now, again, for us, or a limit, I mean, for you guys, that limit was just this thing he brought in when he was doing the slope formula, right? What is that? So we really want to think about just the limit on its own terms. So when we look at this, so I want you to forget about this over here for a second, okay? And just forget about this whole concept. Let's just look at this. What we're saying is that this thing in red is a function, okay? Not the function over here, forget that. This is just a function, right? What's a function? It's got inputs and then outputs, right? What's the input of that red function? What's the input of the red function? H, right? H is the input, and we want to know what this is saying is what is the output as H gets close, the input gets close to 0, right? Again, forget the whole thing about slope and 2 points becoming 1 and all that. Just what does this red thing, what value does this red thing have as H gets close to 0? Now we might say, well, put in a 0. Okay, let's put in a 0. What do we get? 4 cubed is 64 minus 64. We get 0 divided by 0. What's that? Undefined. Oh, that's no good. So we say, well, it doesn't have a value. Okay, but we don't care what the value is at 0. We said as H gets close to 0, right? Now, again, it's hard to totally forget where we got this. Where we got it was, what was H? I keep telling you to forget about it, and then I keep bringing it back up. No, it's kind of silly. So what was H? What was H in the whole slope thing? How far the 2 points were apart, right? And so why were we letting H go to 0? 2 points to become 1. We wanted the tangent line, not the secant lines, right? So the whole reason we let H go to 0 was for that, okay? All right, so now let's forget about that again and come back to this. And so this is just a limit problem, though, that's saying, hey, this red thing has outputs, and it has inputs, which are H, and what are the outputs when the inputs are getting close to 0? Okay, what is if we were to graph this function, they'd be saying, what is the intended height? What is the intended y value of that function? What's that function trying to get to as H gets close to 0? Okay, so back to this.
Let's start by looking at a very simple function graph. What I have here is the function f of x equals x squared, basic parabola. You'll notice that the function changes heights all throughout its domain. That's a very fancy way of saying that the function reaches many different heights based on whatever the x value you're looking at happens to be. For example, what if I look at the function height that corresponds to x equals 2? Well, it's not very difficult to figure out exactly how high that function is going to be when x equals 2, because all I have to do is plug in that x value into the function to figure out what that height will be. So, if I plug 2 into x squared, I get 2 squared, or 4. This means that the function reaches a height of 4 whenever x equals 2. Pretty simple. But now I can create my first very basic limit statement, and that is the limit as x approaches 2 of f of x equals 4. This just means that whenever I'm getting very close to the x value of 2, my function is getting very close to the height of 4.
Okay, now that just seems so obvious, right? It's like, what is the big deal? Why are we doing this? Well, the reason it seems so obvious is it's just a basic function. Nothing weird happens to it. It's just a parabola. It's defined everywhere. And so when x gets close to 2, the y's get close to 4, you say, well, just plug a 2 in. Okay, you could, right? In that problem, you could literally plug a 2 in to get a 4. That's your answer. Some limit problems are that easy. Some limit problem says as x approaches 2, you plug in a 2, you get a 4, you're done. Okay, but those are pretty uninteresting. So we don't spend much time dealing with those. Okay, the interesting ones are the ones like we have. We plug the 0 in for h, and we get 0 divided by 0. That's undefined. But is there still a limit? Are those outputs still approaching something? And a lot of times the answer is yes, there is. Okay, yes, something is going on. Okay, and notice you don't always have to be approaching 0, right? For our special limit, we do, right? Like we were just talking about, our definition derivative, we always want h to approach 0 because that makes the 2 points become 1, right? But what we're talking about here in section 2.3 is just the whole family of limit type problems. All right?
There's nothing really earth-shattering about what we just learned. But that changes when we examine functions that do not reach the heights they intend. Take, for example, this function. G of x equals the fraction x squared minus 6x plus 8 divided by the quantity x minus 2. Here's what the graph looks like. It looks like a plain old line. Or does it? If we zoom in, you'll see that it has a hole in it at the coordinates 2, negative 2. The hole exists because plugging x equals 2 into the function results in 0 divided by 0. And we know that dividing by 0 is a very bad idea. It breaks mathematical laws that we really can't even get into here. However, though this graph has a hole in it, it still possesses a limit when x equals 2. Clearly, the graph intends to reach a height of negative 2 when x equals 2. Even though that graph doesn't actually reach that height, it doesn't matter. The limit still exists, and we can say that the limit as x approaches 2 of g of x is equal to negative 2. This begs the question, when exactly does the limit exist? We examine that in the next module.
Okay, so that one is more like the ones that we were talking about. You tried to plug in a 2, you get 0 divided by 0. Oh, what's going on? Well, if you look at a graph, like they said, clearly that graph intended to reach negative 2. Those y values are getting close to negative 2. They just don't equal it at that point. Well, the same thing for us. We wanted the 2 points to become 1. As the 2 points get closer and closer to becoming 1, we can see what the slope's going to be, even though at that point we couldn't get it exactly. But we can see where it's headed. All right, so I come back to this problem right here. Let's do this problem like they just did. And if you want to get your calculators out and do this along with me, we could. But we could do what they just did. We could take and graph this red function. Right? That's what they just did. They took that green function and they graphed it. And it was a line with a hole in it. Right? Well, we could do the same thing. Let's graph this. Now, when we graph it, we can't use h as our input, right? We have to use what? T. Depends what mode we're in, right? Parametric mode, it's t, but we're going to do it in function mode. So we're going to do x. Okay, so we're going to graph this red function. So we'll come in here to our scratch pad and go on to F1, and we will give ourselves a fraction here. If you hit Control Divide, gives you a fraction, and our left parenthesis, and so I'm going to go 4 plus x, and then I'm going to cube that on the outside of it, and then I'm going to hit my right arrow to get out of the power. You have to be careful of that. Your cursor's still up in the power if you don't hit that right arrow. And then we're going to subtract 64. And then we're going to go down and put x on the bottom. I believe that would be right, wouldn't it? Okay. And so I'm going to graph that. So I hit enter. And, of course, on my picture, nothing shows up. What's wrong? Yeah, my window's no good. Now, I happen to know that if I change the window settings let's change the x to -5 and the x max to 5. What x do I really care about here? What x am I really caring about when x is approaching 0, right? Remember, because our limit said when h approaches 0, and h is our input, h is our x here. So I really care about an x of 0. So I'll just look at between negative 5 and 5. And I'm going to set my y value to about 60. Because we already know it's 48, right? Since we worked this problem, so we happen to know that. All right. So I'm going to set, and there's a little snapshot of that function right there. Now, we want to know, so imagine, just like on the video, what value is this intending to reach as h is approaching 0, or in this case, x is approaching 0? Well, let's go trace. So we'll go trace, graph trace, we'll type in a 0, and we all know what's going to happen, and that is what? It is undefined. Yes, we already said that. When we put a 0 in, we get 0 divided by 0. But clearly, that graph is intending to reach a certain value at 0. So how about we trace at 0.001? And there we get the 0.48.012. And sure enough, at 0, this graph seems to be trying to hit a y value of 48. And that, of course, when we worked it out algebraically, is what we got. All right. Now, another thing we can do on the calculator that's kind of cool to see this same concept is look at a table of values. What if we looked at a table of values right around x equals 0? Well, if you go to your calculator, go to Menu, go down to number 7, which is Table, and then choose Split Screen Table. I think that's your only choice. Okay? You can see this table over here. Now, the problem is I want to look really close to 0, right? Like 0.001, that kind of stuff. So my table is highlighted. You might have to click in there to make sure it's black, because if you click over here in the graph, then it's highlighted. I want to be in the table over here. I'm going to go to Menu. I only have a couple of options. I want the table option, and I want to go down to Edit Table Settings. Now I want to start my table at x equals 0, and I want my table step to be let's do 3 zeros, 0.0001. And then hit OK. And now you look at these table of values. Now I'm going to hit the up arrow a couple of times so I can see on both sides, and you'll see why that's important here in a minute. And so now, look what I got in my table. There's some scientific notation in there. But now I can see x values kind of less than 0. I can see some x values more than 0. And I can see that my y values seem to be getting close to 48. Does that make sense? So this is that concept of limit. Now, we've seen it multiple ways now. We saw it with algebra when we worked out number 43, and it came out to be 48. We saw it with a graph where we traced. The graph seemed to be intending to hit a height of 48, even though it was undefined there. And now we just saw it with a table of values. It's clearly undefined right at 0. We don't care about that. What we care about is what it was trying to get to, was 48. All right, and then one last final note. Since we were doing an extra special limit that happened to be a derivative, we also know that that 48 was the slope of this curve at 4. But for most of section 3, we don't really care about that aspect of it. We're just talking about what does it mean to find these limits. Yes?
So when we graphed the formula right there, why would we able to put an x for each?
Say that again.
Why will we able to put an x for each in this context?
Because forget this context here. In this context, the question is, what is the limit of this thing? It's a function. What are these y values getting close to as these input values get close to 0? So it was just its own function. I wanted to graph it, and the only way we can graph it is use x, not h. So that's what we did. So that's why we put an x in. Okay? But it's important to know, I thought you were going somewhere different with this question. It's important to know that this graph we graphed is not x cubed, right? It doesn't have anything to do with that. It's that thing in red that I had circled there. All right. Let's go to the second video here. When does a limit exist? In other words, are there some times where there is no limit? Are there times where there is no
Now you
limit?
have some idea of what a limit is, and we need to talk about when does a limit exist. To illustrate my point before we get started, let's set up an example. Let's say you and a friend are going to meet for dinner, and you're meeting at a diner that's centrally located between the two of you. If you live east of the diner, and your friend lives west of the diner, and you both want to drive to meet there, Ideally, the roads which lead to the diner will lead you to the same place. If you travel towards the diner from the right, or east, and they travel towards the diner from the left, you should meet up in the same place. Mathematically, this is basically what a limit is. A limit exists if you travel along a function from the left side and from the right side towards some specific value of x, as long as that function meets in the middle, as long as you arrive at the diner, as long as the heights from the right and the left are the same, then the limit exists.
Okay, so think about the graph we just did. And this is really, the most important part of what you just saw right there is the part that it comes from both sides, two cars. The limit, basically what he just said there is the limit exists. There is a limit when from the left and from the right the two cars meet at the same place. And where they meet is the limit. Okay, where they meet is the limit. So that's what you're asking yourself. When you get a question said, especially when you have a graph, because you can really visualize it. If you have a graph and they ask you for the limit, you're asking yourself, where do the cars meet? If they don't meet, the limit doesn't exist. If they do meet, where do they meet? That's the limit. Okay, they're going to expand on that here a little bit.
Now it's time to get down to the brass tacks and look at this mathematically. Take a look at the graph of this function f of x. Visually, you can see that it's got a break in it at x equals 4. So, if we travel towards 4 from the right, we will arrive at a height of 2. However, if you travel towards 4 from the left, you will arrive at a height of 1. This means that no limit exists for f at x equals 4. Let's go back to our diner metaphor for just a second. Notice that as I'm traveling along the road from the right, I end up at a height of 2. But if you travel along the road from the left, you end up at a height of 1. These heights don't match. We won't both arrive at the diner, and no limit exists. We call the height at which we arrive from the right the right-hand limit of f of x, as x approaches 4 from the right. And we denote this with a little plus sign in our limit symbol. Our height that we arrive at from the left is called the left-hand limit of f of x, as x approaches 4, and it is denoted with a little negative symbol. Mathematically, in order for a limit to exist, both the right and the left-hand limits must be equal.
Okay, that's important, that idea of one-sided limit. So when we talk about the limit as x approaches 2, we're talking about both sides. So the cars have to meet. If they don't meet, then we might ask the question, so it might be, give the limit or state that it doesn't exist. If it doesn't exist, tell why. Well, if it doesn't exist, why didn't it exist? The cars didn't meet. So you say, well, the car on the left. Well, you're not going to say the car. But you're going to say the left-hand limit. As you approach x from the left, that's a little negative sign. As you approach from the left, we hit 2. As you approach from the right, we hit 1. They didn't meet. They're not the same. So therefore, the limit doesn't exist. Okay? I really think this car metaphor with the diner, I think, is nice. I think it really can help you because it's really that simple. If the cars meet, the limit exists, and the limit is the y value at where they meet.
Now let's change this function just a little bit. This new function, we'll call g of x, does possess a limit. Can you see why that's the case? It's because the function no longer has a break at 4. Now, there's something to be said here. The previous function did not have a limit at 4. It did have a limit at many other points. For example, a limit existed at 1, at 2, at 5, at 0. All these x values showed locations where the graph did not break. In essence, a graph will not possess a limit if it breaks at the given x value. That's why our new function does possess a limit at x equals 4. Now, let's go back to our diner example one last time. Let's say we're traveling towards the diner. We both arrive at the same location, but the diner isn't there. Maybe it's caught fire or something. Does that mean the limit doesn't exist? The truth is, the limit will exist even if the diner's not there, because you still arrived at the same place. In other words, mathematically, a limit can still exist if your destination is a hole in the graph, because it doesn't matter whether or not the point is actually there. What matters is that you arrived at that point, coming from the right side and the left side. In conclusion, a limit exists on a graph if you arrive at the same height coming from both the right and the left side of the given x value.
Okay, so that's what we were saying here. So the cars meet here at 48, but there's a hole. The diner burned down. It's not there. But the cars meet. They meet at 48 even though there's a hole. So let's talk a little more about a hole in the graph. They're going to talk to you a little bit here in a minute about methods of finding these limits. Okay, the first thing you should always do in a limit problem is you should do direct substitution. So we've always talked about, hey, plug a 0 in for h. Right? Well, you get 0 divided by 0. Those are the only ones we've done up till now. Okay? Sometimes you plug like that one, let x as x approaches 2. We plugged in a 2, got a 4. Okay? And then that was your answer. You were done. So what might happen when you plug in a number? Well, the one we've seen the most is you get 0 over 0. Well, I'll just tell you right now, 0 over 0 means a hole in the graph. And like we've just seen, most of the time when you have a hole in the graph, the limit exists. Okay, if you get 0 divided by 0, there might be a hole in the graph. A very likely possibility. And the limit may exist. The cars will still meet at a hole very often. So you need to keep going, and that's what we've done with the algebra. We keep going till we can cancel something out, and that's common denominator, conjugate, factor, and cancel, whatever. Those are the things we've been doing. Now, if you get a number over 0, like 3 over that number, like 0 is not a number, but if you get 3 over 0 or negative 2 over 0 or 7 over 0 or something like that, then that is a vertical asymptote. Now that's a different situation. And we're not going to get much into that right now. We do that in chapter 4 quite a bit. The cars aren't going to meet, right? So there's a situation where the limit's not going to exist. So for right now, if we do a limit problem and you get like 6 over 0 when you try to plug a number in, just say does not exist for right now. The cars aren't going to meet if you have a vertical asymptote. But if you have a hole, if you have 0 over 0, they are probably going to meet. Okay? And so you need to keep going, and that's the algebra and that kind of thing. One last thing. What's another type of break? That's a break in the graph, a vertical asymptote. What kind of function is going to look like this? Piecewise, right? So it's going to be pretty obvious if you have a piecewise function that you might have something weird going on. You might have a break. This piece ends here, the next piece goes there. Cars aren't going to meet at a break like that. Sometimes on a piecewise, this car hits here and the next one takes off, or the next graph, takes off from that same place. Then the cars would meet, right? So sometimes piecewise functions would have a limit. Sometimes they might not. Depends if you have that break in the graph. That's kind of what they're talking about there. All right, so they've now talked about what a limit means as far as, you know, the intended height, where the cars are trying to meet. They've talked about when does a limit not exist, and we've said, well, that's when the cars don't meet. So you have this break in the graph, something like that. And now the last thing we're going to do is how do we evaluate them? And this is the algebra part. And this kind of goes to what we've been doing. And where I've talked about the conjugate
Once
method,
you
common
determine whether or not the
factor,
limit
cancel.
exists, the next logical step is to try to figure out what the heck that limit is.
So why the
So that's what we'll be focusing on in this section. How do you find a limit? The fancy word for finding the value of a limit is evaluate. So when you see the direction evaluate, basically you should be expecting to get a numerical answer. There are 3 major ways to evaluate a limit. They are substitution, factoring, and the conjugate method. We're going to go ahead and start with the easiest one, which is direct substitution. It is just as easy as it sounds. We'll take an example. Here's one. The limit as x approaches 0 of the fraction x squared minus 1 divided by the quantity 2x plus 3. In order to evaluate this limit, all you've got to do is plug in 0 everywhere you see an x. So we'll put in 0 in the numerator and in the denominator, and we end up getting negative 1 divided by 3. So our limit is negative 1/3. It's as easy as that.
Okay? You always start with direct substitution. Now, on the ones we've been doing, you put in 0 for h, and you get 0 divided by 0 every time. And so we had to keep going. We had to do more. And we did our algebra techniques. All right? But sometimes you plug, like here, you plug 0, you get negative 1/3. That's it. Because what that means is if you graph that function and look at when x is 0, the graph would hit negative 1/3. I mean, there's no hole, nothing weird going on there. The function exists right at that point. Okay? And that's the limit. So that's an easy one. Always try direct substitution.
Unfortunately, not all limits are this easy, and you've already seen one for which that's the case. Remember that function that we were dealing with in the first section of this chapter? In case you don't, here it is again. A limit as x approaches 2 of the fraction x squared minus 6x plus 8, all divided by the quantity x minus 2. We looked at this before. It had a hole in it at the coordinate 2 comma negative 2. And we concluded from that the intended height was negative 2, making it the limit. However, it would be nice to be able to figure out why this is true mathematically. And to do that, we'll have to use the factoring method. As you can see, and as we saw before, direct substitution results in 0 divided by 0, which is not allowed. So we'll have to resort to this new method. We'll use the factoring method because the numerator of this fraction is factorable. If we factor it, we'll get x minus 4 times x minus 2. Can you see why that's a good idea? Well, the reason is because now the numerator and the denominator both contain the term x minus 2, which I'm going to cancel out. This leaves the limit as x approaches 2 of x minus 4. This is much simpler to solve because now you can use substitution. And when I do, I get 2 minus 4, which is equal to negative 2. Remember, we knew the limit was going to be negative 2, and we're right. Feels good to be right.
Okay? So when we canceled out the x minus 2, what was that like that we've been doing? Remember when the h's canceled, right? All that algebra we tried to do when we're doing them the long way was so those h's would cancel because we were plugging a 0 in for h. So when those h's canceled, that was good because that took out the 0 over 0 part. And then at the end, we could plug a 0 in for h. Well, that's what they're saying. When they canceled the x minus 2, that's what was causing them to get 0 over 0 here. So when you get 0 over 0, you say, hey, there's a hole in that graph. There is probably a limit. I need to keep going. I need to do some algebra. So in this case, they did the factor and cancel thing. And so once they canceled out the x minus 2s, now they can plug the 2. 2 minus 4 is negative 2. And now connect that to what the graph was you saw. When they graphed it, there was a hole there. The y values, the cars would have met at negative 2. Okay? That's where you're getting that answer. All right? I really want you to be able to see the different representations of this, what's going on with the limit. All right? On the quiz, we'll do some where we do some algebra. You're going to have a worksheet on those today. There's going to be some where you just give you a graph and you do the limits. That's going to be part of your book homework today. And that's the main thing we're really focusing on today's lesson. Okay, one last method.
If the method fails and the factoring method fails, you're not without hope. You can still try the conjugate method. Before we talk about the conjugate method, though, we might as well figure out what a conjugate is first. Take a look at this expression, the square root of x minus 4. Now, this is a plain old two-term expression. However, it is easy to make a conjugate. All you do is change the negative sign in the middle to a positive sign. The conjugate of the square root of x minus 4 is the square root of x plus 4. That's all there is to it. Now, what if you see an expression like this in a limit problem? For example, this limit problem. The limit as x approaches 16 of the fraction, the square root of x minus 4 divided by the quantity x minus 16. Well, what we'll do is multiply the top and the bottom of the fraction by the conjugate of the radical expression.
That's what we did today on the square root.
Was the square root of x plus 4. Now, the magic of this is that as you multiply out, the numerator will actually become x minus 16. You don't want to multiply the denominator out. Leave them as separate factors. Since I have x minus 16 in both the numerator and denominator, I can cancel them, just like I canceled like terms in the factoring method, and I'm left with a limit as x approaches 16 of 1 divided by the square root of x plus 4. Do you see why we didn't want to multiply out the bottom? It makes simplification much easier. Now I'm able to plug in 16. Substitution works. When I do so, I get 1 divided by 8. So the limit as x approaches 16 of my original function is 1/8. And that's the conjugate method.
Okay, they kind of moved on there pretty quick, but you saw what happened there. Again, multiplying by the conjugate allowed those to cancel, and now then they could plug a 16 on at the end. And they had square root of 16, 4 plus 4 is 8, and so they have 1/8. And there it is. Okay, so that's the conjugate method. But again, the idea is if we were to graph this, and look at an x value of 16, what they skipped is if you plug in a 16 here, you're going to get 0 divided by 0. Okay? So that tells you, hey, I got to keep going. There's a hole in the graph. There's a limit probably where they meet. Where is it? I do the algebra and I find where that is. Okay, so for tomorrow, on your homework sheet, all right, I'll give you the, in the book part, we're going to skip 1 through 3 and number 7. We're going to, those ones I put in the box there, 1 through 3 and 7, we're going to skip those. So Alex, when I walk around tomorrow and somebody says, you told us only to do 1 through 3 and 7, you can remind them that I said skip those, right? Okay, good. Because I can see it, because I'm just afraid. I'm going to go around and say, no, you said to do 1 through 3 and number 7. Skip 1 through 3 and 7. So what you're doing then is 13 through 26. Sounds like a lot, but really what it is just some graphs. It's graphs with piecewise functions. There's gaps and breaks and holes, and they're going to ask you a bunch of limit problems. So it's really just looking at it. Do the cars meet? You know, if they meet, where do they meet? If they don't meet, it does not exist. Or they might ask you, what's the limit from the left? So that'd be, where's the car on the left going to end up? Limit from the right, where's the car on the right end up? So if you're doing them and you think, oh, this seems too easy, you're doing it right. Okay? It should seem really easy. Okay? That doesn't mean it is easy, but if you think there's more to it, there's more to it. If you think it's hard, you're probably making it too hard. Okay? But that's okay. Come talk to me about it and we'll get that straightened out. Then this worksheet here is just some of the last thing you saw there. It's just some practice doing some algebra. Now the first thing you should do, though, always, is direct substitution. So the first limit on the worksheet says limit as x approaches 2. So the first thing you should do is plug a 2 in. If you get out 7, you're done. If you get out 0 over 0, you keep going. Factor, cancel, whatever. All right? I got one last comment to make. This is one in the book. If I've got a graph that does this, and let's say this is a y value of 7, and it's an x value here of 2, and I do the limit of this function as x approaches 2, what are you going to write? 7. You see what I mean about easy, right? The two cars are going to come in, and they're going to meet at 7. So the limit as x approaches 2 is 7. Okay, now let me change it a little bit. Let me put a dot right there at 9. Now what is the limit as x approaches 2? 7. Where do the cars meet? At 7. The diner not only burned down, but they rebuilt a new one at 9. Right? That's what they did. Doesn't matter. The cars meet at 7. So the limit is still 7. Okay, that dot is irrelevant. The function is trying to reach a height of 7 as x gets close to 2. We don't really care what happens at 2. Okay? Now, normal functions are the same. The output and the limit are the same. There would be a case, now that's going to be easy to see. That's going to be a piecewise, right? That's going to be a really weird function. So you'll be able to tell if something strange is happening. Now, one little side note, though. If I ask you in this function, what's f of 2, what would you put? You would put 9. The output of this function at 2 is 9. See, those are two different questions. Now, a lot of times they're the same answer. A lot of times the output and what the cars are approaching is the same thing. But in one like that, they're actually different. Okay? The limit is 7. That's where the cars would meet. Okay. Do the worksheet. And then those some graph ones basically in the book. Again, it feels like for 2 or 3 days I've been really doing a lot of lecturing at you and stuff. So please come in and talk to me about things that are bothering you, that you're not getting. Maybe I've done such a wonderful job of explaining that you just understand.